Yeah, I put on the recording switch.
Okay, so recording is started. Good. Okay, so yeah, so this is going to be your first doubt clearance and tutorial session. I have received some 4-5 doubts about the material posted for this week. Uh, okay, I will come to these doubts one by one. Some of these are yes, some of these are good questions. Some are just small clarification things. Okay, so let me share my window. Okay, so do you see my screen?
Yes.
Okay, good. Okay, so one by one, let us look at the queries first. Then we will solve a few counting exercises. Of course, this is just the beginning of the course, so these exercises are going to be fairly straightforward. But anyway, we need to do certain things. Okay. Actually, the first and the last query is about this statement S7P is prime for all primes P not equal to 7. So just as a recapitulation, I am given some number n. I expand it to the base 7. So it's something like this. 7 are digit L minus 1, DL minus 2, and so on, D1, D0. So it is D0 plus D1 times 7 plus D2 times 7 square and so on until D L minus 1 times 7 power L minus 1. So this is a 7-ary expansion, and here each Di being a 7-ary digit is in the range 0 to 6. Okay, 5 is missing. And once I expand n in this fashion, I say that S7n is just the sum of these quantities, these digits. And so on up to D0. Okay, so if I take some prime numbers here, for example, let's say, give an example of a prime, maybe 73. 73. So let us take n equal to 73, which is a prime. This is 49 plus 24, right? So 21 plus 3. This is correct, right? Yeah. So this is 7 square. 3 times 7 plus 3. Therefore, its base 7 expansion is 1, 3, 3 to the base 7. If I add these two things, three digits, S773, 1 plus 3 plus 3 equal to 7, which is a prime. So this apparently gives a doubt whether if I plug in any value of any prime p here, then S7p turns out to be prime. Okay, the answer is actually this is actually a false statement. Okay.
Yeah, there is one of the One of the students has already posted the answer. He disproves it in the chat.
Yeah, but he didn't give any. Oh. Okay, 16453. These are base 7 expansions or base.
No, sir, this is decimal. Then we will
Base
convert
10.
in.
Okay. Yeah. So one question that was asked, and I found it today. So whenever I have a for all statement, how do I formally disprove it? So that was a question. Okay. So to disprove, we will come to these things in detail later. To disprove a for all statement, only one counter example is enough. Okay, so this is an important thing. Just give a counter example if you want to disprove a for all statement. There is no other formality involved in this proof or disproof, whatever you call it. Okay. So this is important because that was a query. Nothing else is needed. Okay. Okay, I can see many counter examples. A huge number 10000 something like 7 in decimal is the prime with base 7 representation this, and SP is 35. Okay, fine. So we have several counter examples to disprove this. Formally, this settles this issue. Okay, but maybe it's a good idea to see why these counter examples are coming to be so large, like 16453, 11311, and this is something pretty huge. Okay. In fact, I can give you the smallest counter example. That turns out to be 4801.
Yeah, Pranav has written that. Pranav, do you know why it is? Can you give the logic?
No, sir, but actually I wrote a program, so
Okay.
I got the
Okay.
output from there.
Okay.
So that
Sir, I
S7
know.
of P should be of
It will be
6Q,
6n plus minus
6Q
1.
plus
So,
1.
and 6n plus minus 1 as 25 is as the smallest composite of that kind.
25 is the key here. Okay. So maybe the persons who have actually found that magic figure of 25, they already know why, yes, 1, 4, 6 says base 7 is 25. So why is 25 important in this context? So maybe I will just give you a brief I would say, insight why counter examples seem to be not abundant in the domain of small primes. So let us write this P as dl minus 1, 7 power L minus 1, dl minus 2, 7 power L minus 2, and so on. d2, 7 square, d1 times 7. Okay, so give a multiplication sign, otherwise it looks not too good. Okay. So this is my P in base 7 expansion. Now, if I take modulo 6. Okay, then what will be modulo 6? This will be 7 will be 1 modulo 6. So this is 1 power L minus 1, this is 1 power L minus 2, 1 power L 1, and this is also 1. So P is the same as this sum, and which is same as S7P modulo 6. Okay. That means if I divide P by 6 or if I divide S7P by 6, the remainder will be the same. Okay. But since P is a prime, okay, so P is given to be a prime. So if I consider all possible remainders when I divide modulo 6, then I can write P in the form 6k, 6k plus 1, 6k plus 2, 6k plus 3, 6k plus 4, or 6k plus 5. So any positive integer, or for that matter any integer, can be written in this form. These are multiples of 6. These numbers give a remainder of 1. These numbers give a remainder of 2, 3, and 4. Now, if I look at these things, this one, this one, this one, and this one, they cannot be prime because, for example, this is a divisor of 2. This is a divisor of 2. This is a divisor of 3. This is a divisor of 2. Okay. So if P has to be prime, it has to be of the form 6k plus 1 or 6k plus 5, or I can write 6k plus minus 1. Fine. But this P and S7P, they are of the same form when I divide by 6. So S7P is also of the form 6k plus minus 1. So if I now look at small values of 6k plus minus 1, this will be 5, 7, 11, 13, 17, 19, 23, and then 25. So it turns out that a large number of numbers appearing in this 6k plus minus 1 form, this sequence, they are all primes. Only if I can achieve a sum of 25, then there is a possibility to find a counterexample. And since this is 25 and each digit is at most 6, okay, so I need 5 digits at least, because 4 digits add up to 6, 6, 6, 6, at most 24. So I need at least 5 7ary digits. And the smallest such number is whatever you have written, 1, 6, 6, 6, 6. This is base 7. The sum is 25. And it turns out that this number is actually a prime, which is that 4801. Okay. So this is the maths behind it. But for a formal proof that this statement is false, you only give any of these counterexamples. 16453, 11311, or this one followed by many zeros, 7. Any counterexample is more than enough and just enough. Okay. Because this is a for all statement, since this does not hold, this means there exists a prime P for which this is not prime. So you just find out one such counterexample and you are done. I have done this mathematics to show the intuition why it is difficult to find counterexamples when P is small. Okay, is this fine?
Yes, sir.
Okay.
Yes, sir. Take D naught mod 6.
Uh-huh.
Why didn't you take D naught mod 6 in the next page?
This one?
Yes, sir. You took modulo 6 of P. So DL minus 1 plus DL minus 2. At the end, there shall be D naught modulo 6.
Did not. No, everything you divide again by 6, this sum. Yeah, did not modulo 6, that is fine.
No, but D naught is also less than 6, na? So it is just D naught. D naught.
True, but the sum may be bigger than 6.
Some may be bigger.
Yeah. Okay. So this is standard modular arithmetic. Maybe we will come to that later. Okay. So there is no problem.
Sir, I have a query that I know that sum is 25, that S7P is 25. So how can I like trivially arrive at this example 1666?
No, no, this is the smallest number that you need at least 5 digits, right?
Yes.
Otherwise, you cannot achieve a sum of 25. And the smallest thing must be this 6666 and 1, 24 plus 1, 25.
Okay, sir. Means like we
So
have not the smallest such number, and it turned out to be a prime.
Sums are to be a. If it is not, then we have to find. We have to go to further. We have to start it further.
Professor, it's just we're lucky that it turned out to be prime, right? So we could be searching for like a lot of numbers and still turns out to be not prime.
You may call yourself lucky, but anyway, it doesn't matter. If this does not work, then a slightly smaller number will work. But still, it has something like 5, 7 or 8 digits. And 4 decimal digits. Okay. So it's difficult to find, I would say it's impossible to find smaller counter examples. Okay. So that's the I would say nice maths behind this question.
Excuse me. Excuse me.
Why did we do modulo 6? This is just for prime number representation. Why did we do modulo 6? Why not modulo 7 or modulo 8 or something like that? Yeah, 7 modulo 6 is 1, that is true. But what's so special about 6? This is actually some, I would say, some kind of mathematical intuition. Why we will go for modulo 6, not modulo 8, modulo 5, modulo 3. Okay. And my short answer is very unsatisfying to you because this works. That's all.
Sir, I think another major like thing that that actually compelled us to do that modulo 6 is we can actually do one thing, that S7 like P minus S7P. So that every term is having a 7 to the power n minus 1 form. So this will be divisible by 7 minus 1.
It's true.
P minus S7P is 0 modulo 6. So this will actually
True. I understand that is the thing written here. True, I understand, but I cannot give you a better intuition than whatever you are saying. So it is, I would say it is safer to say that I took modulo 6 because this works. That's all about mathematics is. In fact, you think about big integrations that you did in your class 12. And you maybe you made some substitution like x square by cos x, x square e to the power x, things like that. Why did you do that? Because you have the intuition that this will work. That's all about mathematics. This is no different in this current context. You have some insight, and based upon that, you think that modulo 6 will work. and then you actually work out and see that it works. Okay. That's it. There is no difference. Are you dissatisfied or satisfied with this answer? Let us see.
It's not we're not dissatisfied, but I think, sir, if we are like encountering such more types, this kind of problems, then we would be perhaps it will be easy for us to use our intuition to guess which numbers should we use for proving such.
Okay. Intuition will only grow by practice, and it is a deep theorem that when you solve a mathematical question like this, you cannot have any predefined procedure that will allow you to proceed step by step. It is impossible to have any such procedure, mechanical procedure. Okay. So this is reality. You have to live modulo this reality. And indeed, some of these things we will see when you talk about countability and uncountability. And in your flat course in the next semester, you will see more exposure. You will have more exposure to this uncertainty. In fact, I can suggest you. So there is a BBC documentary called Dangerous Knowledge. So this is based upon the life of 4 persons, life and work of 4 persons, Boltzmann, Cantor, Quetelet, and eventually Turing. Okay. These 4 persons together established the so-called uncertainty in mathematical theorem proving and many other things. Okay. They actually established by counting arguments in some sense that I would say the hope of certainty that you are actually expecting when you face an exam is just an illusion. It cannot be there. Okay.
Just to add on, there is also another YouTube kind of a small documentary that math has fatal flaws. That also explains such things.
Yeah, it's impossible. So the guarantee that you expect from us for your tests, exams, we cannot provide because it is theoretically impossible. Okay. So maybe you look at this and if you can also, if you can also give that link for that,
I will share it. I will share it.
Yeah, I will just share it. I had that link. I also looked at that video.
Yeah, I will share it immediately. I'm saying.
Okay, I have already seen somebody has given a link. So it's a very interesting documentary. But this is life. And the kind of assurance that you are asking from us was basically the view of mathematicians in the 19th century or something like that. Oh. Okay. And in fact, you might have heard about a very eminent mathematician called Hilbert. Yeah, incompleteness and all that stuff. Yeah.
Yeah, I tested. Yeah. You see, not everything that is true can be proven.
Yeah. Yeah, so mathematicians thought that whatever is true we can prove, and we will know whatever we can know. Okay, but these four persons eventually established that this is impossible. You know that under any logical framework, there are statements that are true, but you cannot prove it in that framework. Okay, anyway, let's not get carried away too much, but always keep in mind this uncertainty will always be there. This uncertainty is the only certain thing. Okay, and therefore exams will be difficult. Happy or unhappy?
How can they be happy with knowing exams will be difficult? Anyway, let us proceed. I think
Anyway, so
we will cover all this. I mean, don't worry. We will cover this incompleteness and all these things later when we countability and other things we will do. Yeah.
Slowly you will get introduced to this laws of mathematics. Of course, Boltzmann was not exactly a mathematician. He was a physicist. There also we have similar uncertainty. Anyway, let's not worry too much about these things. Okay, so then the remaining questions are focused on this Catalan number deduction and several other issues associated with Catalan numbers. So this is one question. So what we have seen, so we started with an invalid path P. From 0, 0 to n, n. From this we produce a path Q from 0, 0 to n minus 1, n plus 1. Okay. So the construction that I made in the video was a one-way construction. If I understood the question correctly, what about the converse construction? So starting from P, I have generated Q. So what about Q to P? That is, if I want to say all invalid paths from 0, 0 to n are in bijective correspondence or in one-to-one correspondence with all paths from 0, 0 to n minus 1, n plus 1, then I have to do something. I have to show that if I start with, for example, two different paths, I will end up with two different paths Q. Or there is another possibility. I will reverse the construction, and starting from P, I will get Q. Then I will Q, I reverse the construction, I will get back the same path P. Okay. And conversely, starting from Q, I will get P. From P, I will get Q. And this Q and this Q, if they are same, then I believe most of you already know that in that case, we can show that this is a case of bijection. Yeah. Okay. So I just hinted at this reverse construction, the converse construction. So let us start with a path Q from 0, 0 to n minus 1, n plus 1. Okay, so let me draw the grid first. This is the grid. And so this is n comma n. This is the main diagonal. And my point n minus 1, n plus 1 is somewhere here. And I am given a path Q from this point to this point. Okay. The argument goes like this. I start from this point. I will end up at this point, which is above this main diagonal, y equal to x. So at least once, that path q will have to go above the diagonal. At least once, it will have to have, because it will end up at a position above, on the top of the main diagonal. So somewhere it will have to go on the top. Yes or no? This logic is fine, right? Okay. So if, for example, let us look at the first time this thing happens. This path goes to the top of this. It may also happen here. Okay. But anyway, wherever it happens, let us say this is k, then this is k plus 1. Okay. The first time the path q crosses this diagonal upward, it will have to happen, and let's say it happens at the kth instant when the k right movements are. So at that point of time, I have k right movements and k plus 1 upward movements. Okay. I will eventually reach n minus 1, n plus 1 along that path. So there will be exactly n minus 1 right movements. So this is currently done, these many movements. And what are the remaining ones? K movements are done, totally n minus 1, so n minus 1 minus k. And here I have to make n plus 1 upward movements in order to reach this point, out of which k is done. So how many are remaining? N plus 1 minus k plus 1, which is n minus k. But then, like the construction of q from P, after this crossing, if I just make the right movements up movements right, okay, exactly as we have done in the P to Q construction, then the remaining U movements will be right movements and the remaining R movements will be up movements. So the total number of right movements will be k plus n minus k, which is n, and total number of up movement will be k plus 1 plus n minus 1 minus n minus 1 minus k. So k plus 1 cancel. So I will end up in n comma n. Okay. So after this crossing, you simply flip the paths. Right means up, up means right. And then the total count will become n comma n. We can argue that when P and Q split the paths, are a reflection about line y equal to x plus 1. Yeah, it is something like that. Fine. Okay. So are you convinced now? Starting from P, doing that construction, you get Q. P is an invalid path. And starting from Q, you can reverse the construction and get back the same path P. And if you look at this imagery, two reflections will make the path original. Happy or no?
Yes, sir.
Okay. Yeah, fine. So if there is no more question about this query, I will go to the next one, which is more, I would say, somewhat deeper. Fine.
What about the paths which start in the upper half?
Mm-hmm.
They will count.
What?
What about the paths which start in the upper half?
Path is starting upper half means?
First step is U instead of R.
Here. Yeah, then K will be 0.
Means then it may not correspond to a invalid path.
No, this will be invalid path. K is 0, right? I will keep up to this point. After that, I will up to this first overshoot. This I will keep as in the original path. After this, I will change R to U and U to R, not including this. Okay.
Oh, okay.
Okay. That's a confusion. Yes, I understand now. So this K and K plus 1 will keep it as it is. After that, I will just swap R and U. Okay, fine. Okay. Next question, let us come to. This is somewhat, I would say, deeper. So I just mentioned in the lectures that the total number of ways of parenthesizing the product M0, M1, M2 up to Mn is exactly equal to the nth Catalan number Cn. Why? So somebody asked the question, why? How can we establish that the products of these matrices and these paths from 0, 0 to n, comma n, how are they in a sense related? Okay. For that reason, I have prepared this picture and I want to show as an example how this red path, which is a valid path, gives us a parenthesization of the product M0 through M6. Here n equal to 6. Okay. So this will also relate Catalan numbers, matrix products, and also stacky numbers or stacky sequences. Okay. So the idea is something like this. You are given a valid path like this thick red line. This is the valid path. Okay. So this P stands for push. So I will use a stack. M stands for pop, multiply, push. This entire operation. Pop the two top elements of the stack that I am going to use, multiply them, and push the product back to the top of the stack. Okay. So I start this process by pushing M0 unconditionally to the initially empty stack. Okay, or you may think about the stack having M0 sitting at the top, but as the only element. Okay. Then, whenever I have a right movement, so I will look at this. So this is M1. I will push M1. Now I see M2, and once again a right movement. So I will push M2. So the stack at this point will be something like this. M0 is initially pushed unconditionally, then M1 is pushed because this is the right movement, then M2 is pushed because this is a right movement. Now I see an upward movement. So what I will do, I will pop the two top things, M2 and M1, multiply M1 with M2, and push that thing product to the top of this stack. Then I once again see a rightward movement. So this is M3, so I will push M3. So the stack will now become M3, M1, M2, M0. Then I see two vertical movements, upward movements. So I will take this thing out, multiply and push the product M1, M2, M3, M0. This is after the first vertical movement. Then what I will do, I pop this, multiply this with this and put the product. So it will be M0 times M1, M2, M3. Okay. Then there are three horizontal movements. M4, M5, M6, they will be one by one pushed to the top of the stack. So it will be M6, M5, M4 after these two horizontal movements. And then there is again a product business. So this will become, this thing will stay, the big thing, M4, M5, M6 after the first. Then you multiply M4 with M5, M6 and you have the same quantity, this big thing here. And in the final step, you will have the final product M0, M1, M2, M3, M4, M5, M6. So do you understand the construction? Yes or no?
Yes.
Okay. So this essentially establishes the connection between valid paths and products like this. And then you have to formally establish that this is once again a one-to-one correspondence between the set of all valid paths and all parenthesized products of M0 through Mn. Okay. So this can be done, so I leave it to you, but this construction is important. And also you see, I am essentially doing things like whatever I am doing in this stacky sequence. This is push, push, pop, push, pop, pop, push, 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 pop, pop, pop. And just before pop, you are printing something, the top of this stack. So this I would say construction also indirectly proves that why stacky sequences are also the same as Catalan numbers or these valid paths or matrix products. Okay. Here's the question. This multiplication isn't associative? Yeah, it is associative. Matrix multiplication is associative. So this explicit parenthesization essentially says that I will first multiply M1, M2. Then I will multiply that thing with M3. Then I multiply that with M0. So this is a computational way, or this will give you a sequence of multiplications. Of course, you may first multiply M0 with M1 and then with M2 and then with M3 and then with M4 and so on. By associativity, you will get the same product. That is true. But this explicit parenthesization actually tells you how you compute the product. Whatever way you do it, you will get the same final result by associativity. That is true. But this explicit parenthesization gives you a computational handle. How I proceed? Is that okay? Does it answer your question?
Yes, sir.
Okay, good. Okay, so that is how this, valid paths, matrix products, stacky sequences, and all these things, these are related. And in fact, if you draw what is called a expression tree for this, you will immediately see that the binary trees are also somehow related to this Catalan numbers, matrix products, and all that stuff. Okay. Anyway, let's not worry too much about binary trees because I think it is still not covered in your algorithms course, which has just started. Happy or not?
Yes,
Sir,
sir.
I have a doubt.
You still have a doubt. Okay, tell.
Sir, in the last M operation means after we have popped the means we are multiplying M1 with M2, then we are multiplying with M3, and then we are multiplying the result by M0 pre-multiplication. So this result as a whole is multiplied with the second term, right? M4, M5, M6. Means I am unable to understand the order in which the last stack which you have drawn. Shouldn't there be a parenthesis, one more set of parentheses because order will.
Yeah. So you mean this one? Yeah, that's true. Yeah, it should be there. Otherwise, it becomes ambiguous. Yeah, you're correct.
Yes, that was my doubt.
Yeah. Okay. Fine. Okay. So this is why these things are related. Then there is a final question, final query about Catalan numbers.
This will be covered later in details.
This will be covered later, but I can, for the moment, just give you an idea how this matrix product kind of stuff can give us an idea. We will look at this question in detail later. So let us look at multiplication of M0, M1, M2, Mn. And let us look at Mi plus 1. And let us say this is the last multiplication. Okay. So then I will look at in how many ways I can parenthesize this, in how many ways I can parenthesize this, and that will be Ci, and this will be, I believe, Cn minus I minus 1. This is correct, right? I plus 1 to n, how many are there? N minus I. So n minus I minus 1. Okay. And I can vary from 0 to n minus 1. So this essentially says Cn is...
Sir, sir, in the left side, it should be I.
N minus I plus 1.
No. Y plus 1. 0 to I. I plus 1 elements are there, therefore I.
No, yeah, I got it. Sorry, I was.
And this I ranges from 0 to n minus 1. Yes, 0 to n minus 1. So this is what is called the recurrence relation for the Catalan numbers. And when we study generating functions, we will see how we can solve this recurrence relation. Okay, so we will solve this later. It requires generating functions and some lots of calculations. But this recurrence is quite important for Catalan numbers. Anyway, we will once again come to this question. Happy or not?
Hello, sir.
Yeah, yes.
Sir, about the recurrence, sir, I was also thinking that about that figure that you have drawn, that when to go from 0 to 0 to k comma k plus 1, and for going from 0 comma 0 to k comma k plus 1, there is c of k, means c of k number of paths, right? Means by following the condition.
Which one? No.
K comma, yes sir.
This one?
Yes sir. For going 0 comma 0 to k comma k plus 1, there are c of k paths, ck paths. Yes sir.
Ck paths, yes, because this is known to be a positive movement. Yes, okay, fine. Then?
Sir, then to find c of n, we can use the recurrence of like summation of c of 0 to 0 k means n minus 1. Like for this k comma k plus 1, if we reached k comma k plus 1, we know that it is an invalid part. So now from
yeah, this is an invalid path. So it's the number of invalid parts is not exactly ck.
Yes, c of k into any free path from k comma k plus 1 to n comma n, like any path. Means
I exactly do not understand your suggestion, but this way also you can view it anyway. Because if you touch something here, that means, again, in terms of this imagery, here I have touched that diagonal, right, y equal to x. So at that point of time, I have only one thing in the stack, and the remaining thing. So similar things happening path level also. Anyway, yeah. Okay.
Sir, here in the recurrence relation, we are assuming that there is a bracket around mi and mi plus 1.
Yeah.
But sir, in the cases it may be possible that there may be more numbers with them in that bracket.
Wait. So I am assuming that the last multiplication is something like this. Then I have to fully parenthesize this and this. And then I will vary I from 0 to n minus 1. So what is the question exactly? I do not understand.
Okay, sir, now
No, yeah, I think he has missed the point that the sum varies from 0 to n minus 1. So the middle point can shift from 0 to n minus 1 anyway.
So this is one particular case.
Yes.
But then I will
yes, sir, no.
Okay, so this is more or less all the query items that I wanted to discuss.
Sir, I actually I have a query. This is just a corollary of this Catalan numbers thing. Sir, what if we impose a further restriction that it should not even touch that y equals to x line? So how can we derive in that case if it's possible?
Yeah, this is an exercise we will solve. I don't know why you ask this question. This is actually an exercise we will solve. But it is already 1 hour. So I will first show you some exercises. Then let us have a small break, maybe 5 minutes break. And during the break, you just think about. So some of you may be in our PDS Spring 21 course. Are there any person?
Yes, sir.
Okay. So there actually we have given a programmatic way, write a recursive program to find several things. So you have given R, you are given R red balls, G green balls, B blue balls, and you have to programmatically find out how many arrangements of these balls are possible subject to certain constraints. So precisely these are the 4 constraints. All blue balls appear together. The arrangement starts with a green ball and ends with a non-green ball. No 2 red balls appear together. No blue ball can appear after a red ball. Okay, so these are the 4 parts. Do you remember? Whoever has gone through. Okay, so for the moment, so we have given some names, right? All blue, G, no G, and some things like that, the function names. And now we want to find explicit mathematical formulas for these counts. It's not necessary that you have to write a code to find out these numbers. Okay. So all these 4 counts can be derived mathematically, so you think. Okay, and then I will come back some 5 minutes, something like 5 minutes later. Okay. So hello, I am back. So have you thought about this? Okay, let us one by one try to solve. Part A. Any suggestion?
R plus G plus 1 factorial by R factorial G factorial.
R plus
G plus V plus 1 by R factorial G factorial.
Yes. So this is easy, right? Because since all the blue balls appear together, just treat them as a single object. And then you have R balls, R red balls, G green balls, and one object like all blue balls together. So the answer is R plus G plus 1 factorial over R factorial G factorial. And 1 factorial is there that you don't need to worry about. 1 factorial.
Sir, all red balls are identical.
All red balls are identical. All green balls are identical. All blue balls are identical. Yes. This is fine, right? Because all blue balls appear together, I can treat all the blue balls together as a single object. Okay. So what about this?
G plus R plus B minus 2 factorial by G minus 1 factorial R minus 1 factorial B factorial plus G plus R plus B minus 2 factorial by G minus 1 factorial R factorial B minus 1 factorial.
Okay. So I believe you understand it. So it starts with green and ends with either red or blue. Okay. So then, if this is the case, green, red, then what is this? What are the remaining things? G minus, okay, how many red balls? R minus 1 red balls. How many green balls? G minus 1 green balls and B blue balls. And in this case, you have R minus R red balls, G minus 1 green balls, and B minus 1 blue balls. This will happen except the end positions. So you just count this. So total of this is R plus G plus B minus 2. Factorial over these things, R minus 1 factorial, G minus 1 factorial, B factorial plus this count. So once again, R plus G plus B minus 2 factorial, R factorial, G minus 1 factorial, B minus 1 factorial. Okay.
Yeah, Archit, your suggestion is also be there. That's an alternative solution.
Yes, yes. Minus, you can also do this minus thing. Yeah, that is also fine. This is also fine. Yeah. Yeah, this is also fine. Start with brincusses minus start and end with brincusses. Yes, this is also fine. Yeah. Okay, so this is a simple thing. So what about this? No two red balls appear together.
G plus B factorial by G factorial B factorial, G plus B plus 1 CR.
So this is similar to abracadabra thing, right?
Yes.
Okay. So you know two red balls appear here. So you
There should be a case that like red ball should not be greater than the sum of blue plus green. Otherwise, it is.
yeah. Let me write it down. Green plus B, G plus B factorial. This is the total number of ways of arranging green and blue balls, and then I will insert these red balls in between or at the end, but without repetition. So how many positions are there? G plus B plus 1, and I have to choose any R of this. Okay. So then somebody raised the question, what happens if R is bigger than this quantity? R is greater than G plus B plus 1. Then what is this combination?
Zero. But in this case is not possible.
Not possible. Yeah, you cannot choose R elements without repetition from G plus B plus 1 if R is bigger than this. So this choose thing is 0. So the quantity is 0. 0 times whatever, that is 0. So there is no contradiction, right? This formula correctly, I would say, characterize the count. Yeah, then the final question is also not very difficult. No blue ball after a red ball.
R plus G plus B, choose G.
Okay, I believe you understood this. No blue ball after red ball. So that means all blue balls will appear before all the red balls. And then I will put the green balls. Here, 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 here. But this time it is repetition, which is allowed. Okay, so how many positions are there? R plus B plus 1. How many elements I am choosing? G. Right. So this will be G minus 1. But this is combination with repetition. So it should be G. This plus this minus 1, choose G. Correct, right? So R plus B plus G, choose G. Happy or not?
So doesn't the question mean that no blue ball appear immediate after red?
Not immediately. So if a blue ball has if an R ball has appeared after this, so here or here or here, after this no blue ball can appear. So that means all the blue balls will appear before all the red balls.
Sir?
Tell.
Sir, I have a question on the abracadabra question that you mentioned. Sir, in that question, you are in one part you asked us to find the number of ways in which no two A's or no two B's appear together.
Yes, I know this question was raised last year. Yes, this exercise, this becomes actually very dirty. So to try to figure out, idea is that initially no A's appeared together. So I just added the remaining things and just inserted A without repetition. But now since I will allow B to be added later, sometimes repetitions are allowed. I can take something like this and later I will introduce B here. Okay. So that will essentially lead to too many cases, and the, I would say, computations become very dirty. Okay. So how many A's are there?
5.
5 A's, right? So you have to consider many cases like A, things like that. Many cases you have to consider, and the calculations become really dirty. Okay.
Okay, sir.
Yeah.
Sir,
What
why is there G minus 1?
Which one?
The G minus 1. The there only.
No. Do you remember that formula? N elements, you have to choose R with repetition. N plus R minus 1, choose R. So that is the formula, right?
Oh, okay, sir.
Okay, so this is the N in our case. This is our R. This formula I have just used. Yeah, so there are many other questions. So I have just picked these 4 because these 4 were part of this PDS question. There are many things. So some of this can be easily derived, some may be very difficult, like this. If I say no 2 red balls and no 2 green balls appear together, then this becomes very difficult. Okay. Yeah. So it's some of these questions can be easily answered, some become very difficult. Okay. So let us switch to some other thing. How many sorted arrays of size n with each element in the range 1 through R? This is also not very difficult, but just figure out why.
RCN.
No.
So you can take that number of times 1 appears, number of times 2 appears. The solution of x1 plus x2 plus xi equal to n, the number of solutions.
Yes.
So n plus r minus 1 choose r.
Yeah, something like x1 is the number of ones, they will appear first, then x2 number of twos, x3, xr equal to total number of numbers will be n. Will be n. Where each xi is greater than or equal to 0 and a positive non-negative integer. So as many number of solutions are there for this, and that turns out to be how much? N plus r minus 1 choose n. A dot R.
N.
That is fine, right? Because we're choosing n elements with repetition, so n. Yeah. Okay, so this is just another way of looking at that equation. Okay, convinced, right?
Oh, yes, sir.
Okay, good. Then, again, this is the same question, but it is slightly more involved. How many binary strings of length n are there with exactly k occurrences of the pattern 0, 1?
Sir, 2 to the power n minus 2k.
Oh, to the power n minus 2k. Why do you think so?
So because, sir, 2k patterns are, I mean 2k positions are fixed, so the rest of we can either fill it with 0 or 1.
Positions are not fixed.
Okay, sir.
They are not fixed. 0, 1 may appear anywhere.
Solve x1 plus x2 up to so on means x of k plus 1 is equal to n minus 2k.
Okay, this is a better way of looking at it, but there are some small.
Sir, n choose 2k?
N choose 2k, no. No, tell us something. Why you think that is the case?
Sir, we can divide the string into chunks of zeros and ones. So it can be the case that it has exactly k zeros and k one, like k ones, or it has k plus one ones and k zeros.
Yeah, not very clear. There is another suggestion. Choose n out of r. What is r in this context?
So it was the reply of previous.
No, it was the reply of the earlier case.
So in this, we can assume that we have k. We can place 0 1 k times. So there are k plus 1 gaps, and so it is kind of x1 plus x2 up to xk plus 1 equal to n. So we can choose n out of k plus 1 with repetition, and for each when we are choosing.
Okay,
so
okay.
we can place all zeros or all ones.
Okay, true. I told you, you are on the correct line. But still there are a little bit incompleteness in the solution.
So what's wrong with the solution with x1 plus x2 plus so on till xk plus 1 equal to n minus 2k, because that seems right.
I will tell. Think little bit. I will tell. Yeah, the idea is fine. I will do similar thing, except that it will not be k plus 1. It will be 2k plus 1.
Sir, so like there is a condition that when we arrange them, that other 0 and 0 ones might also form 0 and 1. So we have to remove that case.
Yeah. No, first of all, let us see. You have exactly k occurrences of 0, 1. 1 occurrence, 2 occurrence, 3 occurrence, let's say k minus 1th occurrence, the kth occurrence. So that gives you a total of 2k positions where this will happen. Before that, before the first occurrence of 0, 1, I may have things like this. Any number of 1s followed by any number of zeros. That will not introduce a new 0, 1 pattern. Happy or not?
Yes, sir.
Okay. Here also I can introduce any number of 1s, any number of zeros. That will not introduce a new 0, 1 pattern. But I can have any number of 1s here, any number of zeros followed by any number of zeros. Happy? Similarly, here I can have 1 star, 0 star, 1 star, 0 star, 1 star, 0 star, and at the end I also have 1 star, 0 star. This, 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 this. So let us say there are x1 number of ones here, x2 number of zeros here, x3 number of ones here, x4 number of zeros here, x5 number of ones, x6 number of zeros, and so how long will it go? So this is the k minus 1 occurrence. This is occurrence number 1, occurrence number 2, occurrence number 3, occurrence number k minus 1. This is occurrence number k. So 1, 2 before 1, 3, 4 before 2. So before k I already have x 2k minus 1 plus x 2k. At the end also we will have 2k plus 1 x 2k plus 2. So this is the remaining part that you want to fill. So that will be n minus 2k. Agree or not?
Yes.
Okay. Yes, sir. So these many positions you have to fill with ones and zeros, but in this particular fashion. Okay. And what will be the count? 2k plus 2. So n minus 2k plus 2k plus 2 minus 1. Here what will you have?
N minus 2.
N minus 2k, right? These many elements you are choosing. Okay, n minus 2k. And this will be 2k will cancel, 2 minus 1. So n minus 1, no, n plus 1, right? Is n minus 2k. And in fact, I will write it this way for a reason. N plus 1 minus 2k plus 1, right? 2k plus 1, yeah. Happy?
The first D should be 1 now, sir, in the binary string.
What?
In the binary string, the first one should be 1 now, sir. X1 should be greater than or equal to 1.
No. It may start with 0.
Sir, then the end of the binary string will be less than n, no, sir.
No. Binary string means any sequence of zeros and ones. Don't confuse with numbers. 000 is a binary string.
Okay, sir.
For the moment, it has nothing to do with the number 0. Any sequence of zeros and ones. Happy?
Then to represent 0, we should represent it like 0, or we can represent that 000 in binary form.
No.
No, I mean 0 and 000 are two different binary string of length 1 and 3 respectively.
Yes. I am not viewing them as numbers.
Okay.
Strings and numbers are not exactly the same in this context. Okay.
Yes, sir.
Okay, of course there is a relation between this thing, but let's not worry too much about this. Okay. So the next question is something a little bit peculiar.
Professor, can we use like binomial theorem to prove this?
You want to use binomial theorem? Okay, there are many ways you can prove it. But there is a reason why this exercise is here. Of course, this can be proved in 100 ways, maybe 1,000 ways, many ways. There is a reason why this appears immediately after exercise 3. Let us look at the solution once more. Oh, sorry. I have changed this plus to minus, so it should be in plus 1. Yes. Sorry. So look at this final solution and this expression. Can you correlate these two?
So sum of all the possible solutions for all values of k.
Okay. So sum over all k. So that is maybe 0 occurrence of 0, 1, 1 occurrence of 0, 1, 2 occurrence of 0, 1, up to n by 2. These many occurrences. No further occurrences are possible, and then you will get all possible strings of length n, and that is 2 power n. On this side it is 6. Okay, so there are many other ways. For example, you may think about proving it using binomial theorem or some other combinatorial argument. Okay. But in the current context, this immediately follows from the previous exercise. Okay. So you may try other things like binomial theorem. You may also try to use other direct combinatorial argument. Okay. And there may be other proofs also. Okay. That is about these permutations and combinations. Then let me ask this question, which somebody for some reason already raised. How many paths from 0 to n comma n? Of course, only allowed movements are right and up that do not touch the main diagonal except at the start and at the end. Somebody raised this question, right?
Yes, sir.
Yeah. Let us now answer this.
Sir, I have done it as it's coming Cn minus 1.
N minus 1, right? Why?
Sir, we can consider as a subgrid of that grid, because the initial position starts from 1, 0 and ends at n comma n minus 1.
Okay, so this is actually an easy question.
Total number minus the way it is touching by 2.
So from 0, 0, we will go to n comma n. This is the main diagonal. And your path will not be allowed to touch this except here and here. So that essentially means that the first, anyway, in any case, the first movement is right and the last movement is up. Okay. And if I look at this, so the original Cn type of thing, I am allowed to cross this line, right? But I am not allowed to cross this line. But in this exercise, I am not allowed to cross this line. So essentially, I have to go from 1, 0 to n comma n minus 1. You know how many ways you can go? This is basically an n minus 1 by n minus 1 by 8. So the answer is C n minus 1. Happy, right?
Yes, sir.
Yes.
Sir, in the previous question, in the fourth question, I didn't get how did you find the sum to be 2 power n?
What is 2 power n? This is the total count of all possible binary strings of length n. No? Because in the first position you may have 0 or 1, in the second position you may have 0 or 1, in the third position you may have 0 or 1, and you have n positions. So it is 2 times 2 times 2. It's an n-fold product of 2 power n.
Okay.
Okay. Yeah. And this is fairly straightforward. I think this is the last exercise, so let us do it. And
yeah, somebody during our this session in the beginning has raised a question in the form that some derivations of Catalan number is he cannot understand. So could you please clarify that what is his doubt? Then we can.
Is there a new query?
Yeah, there is just a new query that the derivation of the Catalan number. Kindly do that again.
No, sir, I understood.
Okay.
I doubt.
Okay, fine. That's fine.
Oh, okay. Yeah. Do you still have a doubt? Because we have already talked about it.
No, sir. The second one you explained is my doubt.
Okay. Thanks.
Okay. So that query is answered anyway, right? For you. Okay. No problem. Okay. So now let us solve this last exercise for today. How many paths from 0, 0 to not n, m, n, where m is greater than n, such that, so let us draw the picture. So m is greater than n. So it will be something like this. You start here, end here, and you never have more up moves than right moves. So that means if I draw this y equal to x line, your path will never go to this, on the top of this line. Okay, so this is 0, 0. This is m, n. And this is basically n, n. So this region has to be avoided. All the paths will be in this unshaded region.
The number of paths in that is simply the 2ncn minus the 2ncn by n plus 1.
M does not come into picture.
Like the number of paths that are not to be avoided is same as the one we found in Catalan. So it will be m plus nc m minus 2ncn by n plus 1 into n.
No.
So, in one part, the final destination was n, n, but
Yes. So that is the reason this counting is not fully correct. Idea is fine.
M plus n factorial by m factorial n factorial minus cn.
All traversals minus cn minus 1. No, that's the question. That is not incomplete. Because cn minus 1, why n minus 1?
Sir, all traversal minus cn.
Cn. No, that's the problem. All the cn paths or invalid paths, they will start here, cross somewhere here, and end here. So you do not account for a path like this. Maybe I use another color. You start here, go here, but instead of reaching this point, you reach here. So these things are not counted in your Cn minus 1 or Cn.
Professor, can we set up like a summation as in first one right move, then Catalan along the diagonal, then another right move, then Catalan along the diagonal. So they're all distinct cases. Can we try that?
Yeah, you can do many things. But this is fine, right? Why this all paths minus Cn will not work? Right. This path is unaccounted for in your CN, whatever you are subtracting.
Sir, can we proceed in a similar way like we proved the Catalan? Means it first occurrence at k comma k plus 1, and then we can just mirror the path, and then we can subtract the from the total paths the number which we obtain.
Exactly. That's, I think, the best way of doing it. Yes. So follow the proof or derivation of derivation of CN. So that means total number of paths is m plus n. Choose m or n, whatever you say. Total number of moves is m plus n, and you choose m horizontal movements or n vertical movements. This is total number of paths minus, let us see. So if there is an invalid path, then for some k, I have k right movements and k plus 1 up movements. Okay. So let's say this is the first time this thing happens. Okay. So how many right movements are remaining? M minus 1, right? And how many up movements are remaining? N minus k minus 1. No, m minus not 1, no, m minus k. K made, total will be m, so m minus k, and this will be k plus 1, n minus k plus 1. But then after this, you do the similar thing. You swap r and u. So this will be this will be this. So where do you end up? So swap r and u after this, and then you will end up in
n minus 1 comma m plus 1
at k n minus 1 comma m plus 1. Conversely, if you end up somewhere here, and then you can reverse the construction exactly as in the derivation of Cn. So total number of paths from here to here, 0, 0 to this. And so this point n minus 1 m plus 1 will be somewhere here. N minus 1 m plus 1 somewhere here, right? So it is on the top of this y equal to x line. So you have to cross it somewhere and then again reverse it, blah, blah, blah. So it will be m plus n. Choose m plus 1 or n minus 1, whatever you like. Happy?
Yes, sir.
Okay, that's it. So today's exercises are actually easy because it's just elementary counting. Yeah, anyway, it's already 11:50, so.
Can you go to the fourth sum?
Which one?
Sir, here only, while telling that we have to do minus Cn, I thought that in the region you shaded, we can consider all the invalid regions being there only. Means it cannot come below x equal to y equal to x.
True. But in your Cn, you are counting, you are stopping here. But now you are stopping here. Your destination is different.
Oh, okay, sir. Okay, sir. Yes, sir. Thank you.
That is the difference.
So can you go to the fourth sum?
Fourth one.
Yes, sir.
Yeah.
So like how are you relating this sum to the previous one? I can't understand that one.
Okay. So here I am assuming there are exactly k occurrences of 0, 1. Okay. So k can be 0, 1, 2 up to n by 2. Floor of that.
Yes, sir.
This much is clear, right?
Yes, sir. Yes, sir.
Okay. And I know for each k, the exact count is something like n plus 1, choose 2k plus 1.
Yes, sir.
Right? This is what we have derived. So put k equal to 0, it will be n plus 1, choose 1. Put k equal to 1, it will be n plus 1, choose
Yes, sir. That,
3.
okay, so that kind of it.
So that explains the right side. And left side is the count of all possible strings of length n over the alphabet 0, 1.
Professor, will we be getting extra tutorial sheets for this?
We'll be uploading it in the web course page. After the tutorial, we usually upload it. And there we will also give some more problems for you to think and try.
Yeah, it will be similar problems, but you just work out.
The problems that we solve in every tutorial, we will usually try to give the solution as well, if possible, in the uploaded sheet, and also add some more problems so that you can also have your own time to go through that also. Okay.
Okay, sir.
Okay. Yeah. So fine.
I think we are done. Apart from only one question somebody has raised, we have not answered. You can try. He has made that what if the question was blue ball is not after red but immediately after red. No, blue ball is immediately after red.
I have seen this. We have to think. I don't know. Immediately, I do not know.
You also can think. We just have to see all possibilities and try to figure out a solution.
Yeah.
I mean, one way to think as it comes to my mind is that you can see the RB string should not occur in the all possible strings. The occurrence of RB should not be there.
Yeah. Yeah. Oh, that's yeah. This can also be maybe yeah. Yeah. So you tell if you have any further queries, let us know, or let us call it a day.
Sir?
Yeah, yeah.
So I have a question in partition topic. A partition topic.
Partition topic.
Sir, you have where you have derived n plus r k minus 1 c n, that x1 plus x2 plus x3 is equals to n, and it can be a non-negative number x. That formula one.
Yeah, 2 power n minus 1. That formula, right?
No, sir. Where means x1 plus x2 plus x3 so on up to xn is equals to k, and xi can be is a non-negative integer. So how many possible ways? So the formula n plus k minus 1 c n. So in this lower bound of xi is given. So can we solve if the upper bound of xi is also given, like in in using pen and paper only? Means no.
Okay. Upper bound. Yeah, you say xi greater than equal to 0 or greater than equal to 1.
So we might have to do principle of inclusion exclusion, take different variables.
But xi less than equal to 5, let's say. x1 less than equal to 5. Then definitely you can use this formula straight away. That's not possible, right?
So if there's just one variable with a condition, then it's easy, right? Because we can remove the upper half of the solution.
Yeah, then you can actually take for x1 equal to 1, x1 equal to 2, 3, 4, 5 individually. If it is a condition for all of this.
Sir, what if we multiply both sides of equation by -1? then inequality will reverse.
Oh, but you also have something. You have both this. Okay, let me write.
But then we wouldn't be able to count. That's the issue.
I want to have something like x1 plus x2 x n equal to r less. And I have some lower bound li less than equal to xi less than equal to some upper bound uy. Definitely you cannot use the formula in this context. So one possibility is you can use something like generating functions. Possibly. Yeah. Yeah, so you cannot use. For the moment, let's say that you cannot use that combination with repetition formula. Definitely you cannot use. How to do? Maybe we will see. Yeah.
So the upper you can make the lower bound at a certain value so that a single variable doesn't crosses the upper bound.
Yeah, if there is a single variable, I can see a suggestion. Xi less than equal to 5, then answer is total minus when xi is greater than equal to 6. But then if this condition is on all of this xi's, then this will be.
In that case, you can make a lower bound which is big enough so that one of the variable doesn't crosses the upper bound. A lower bound for all, we can give it.
Then we miss solutions.
No, this is true. This is for xi only, one variable. If there are multiple variables, for example, I say 1 less than equal to x1 less than equal to 3. 0 less than equal to x2 less than equal to 4. 2 less than equal to x3 less than equal to 6. Okay, something like that.
Sir, one way to do it would be to take powers of x, which correspond to the lower and upper bound, and then
multiply.
Yeah, and then multiply it so that the net.
So that is what is called generating functions. We will study that later.
Yes.
Yeah, I will study that later. Yeah. But you cannot use the combination with repetition formula. Straight away.
I think without generating function, it is difficult, I think.
Yeah. Yeah.
Okay, I think you also think, we will also think if we can have a counting argument here.
Yeah, good. Any other question? Yeah, it's 11:59.
Yeah, so I am just stopping the recording. We are done almost.
Yeah, so we can stop the recording now. Yeah.